Well, hello everybody. I'm going to go ahead and get started. My name is Steve McQuarry. I'm from Equinix. Been there for many years, since the beginning of the company. I've also worked at AT&T, Ericsson, and University of California, San Diego, supercomputer and manager of Datacom. So, been in the business too long. I guess time to retire, but for a long time. Anyway, welcome. Today my talk's really on the intro to timing. Not really going to talk about vendors, going to be vendor neutral. Just talk about timing. The question always comes up, why? Network timing. And I always like to say this, timing's not for the traders anymore, it's for the networks too. And I heard this radio documentary the other day on Bernstein, and he was talking about trying to sync the orchestra up. And it was funny, he was talking about latency with part of the orchestra in the back as opposed to the orchestra in front, and figuring out where to put his baton so that in time the orchestra would respond. So I thought, oh yeah, this is just like time, trying to sync the whole thing up. So that's what the conductor does in the orchestra. Nobody knew. He's trying to sync everybody up. But it was interesting hearing this talk about dealing with latency with the orchestra and timing. So that was very, very profitable or very connected or very synced to this talk. Well, let's start back with network synchronization. Back where the telco operators from the office to the CPE. In this drawing, as you can see, you had clock at the central office, basically over TDM circuits and synchronizing all that. And things have moved out now to the wireless towers and so on. The point is that a variety of equipment is connected and is used for these elements for function. And they all have clock or oscillators and require synchronization for ultimate network performance. The clock circuits in these elements are designed for system purposes and usually are lower quality oscillators and deal with phase lock loop circuits and use elastic buffers to compensate for timing differences. So in the old standard, the ANSI T1.101 and other industry standards require nominal frequency accuracy across networks of 1 to the 10 time 11 or better. These clock circuits don't operate at that level, so they must be synchronized to a common clock. And that's kind of what this drawing here is showing and where kind of all this came from in the telecom days. And this slide here says it even better. So we had telecom synchronization in the telecommunication networks, the process of aligning the time scales of digital transmission and switching equipment so equipment operations occur at current time in current order. Synchronization is especially critical for real-time services such as voice and video, and of course the impacts of poor synchronization. Call setup, take down, management problems, degraded speech quality, audible clicks, degraded data traffic throughput. A lot of us have seen a lot of this. Freeze frames and audio pops on video transmissions, call disconnects during mobile call handoff. Boy, that never happens. And partial and complete traffic stoppage. If you've seen really poor synchronization, I've actually seen a data network just stop working, just stop. Synchronization requirements. Frequency synchronization, phase synchronization, and time synchronization. And these are just some graphs I drew to kind of show these three principles that are very important to have in a network. Stratum levels. Performance levels or stratum as specified by ANSI or Telecordia. Telecom networks should always be traceable to stratum 1. The Office Prime Reference Source, or PRS as we know it, Holdover is the ability of the system to maintain frequency accuracy if Stratum 1 reference timing has been lost. And of course, a slip, a measure of synchronization error. It is a frame, 193 bits, shift in time difference between two signals. So I built this chart to show, because there's a lot of clocks that people have been familiar with. Stratum 1 coming from cesium, GPS, the old cesium gas clocks that are around. I still have 2 of these running in a network. Of course, GPS, going out to your GPS antenna. 2, rubidium, an oscillator. 3E precision quartz. You can find the 3Es usually in ONS and DMX, Alcatel-Lucent equipment. In fact, a lot of operators will just use that controller card or that in their equipment and just stay at Stratum 3E. Of course, the other one is Stratum 3 transport, and then 4, of course, CPE. I wouldn't recommend anything past 4, but 3 and up is, usually 3E and up is what I've seen operators be using in the networks. This diagram, I actually took a clock that I have, a clock module, and it's interesting when you've, if you haven't worked with clocks before, they have to warm up. Clocks have to warm up, and sometimes it can take 20 minutes, it can take an hour, it just depends. But as you're working with the clock, it's got to warm up. It goes through these phases, acquire valid reference. It's looking for reference points. And what you're looking for the clock to do is lock. And that means normal state, time it takes a quality input reference. So your clock is usually connected to a time source, be it CDMA or GPS, whatever. And it's got to lock, warm up and lock to this, because this, remember, is an oscillator. Holdover is when your clock is not connected to your time source anymore. And it's going to it's just going to go to holdover and be the oscillator. And of course, free run, time will return to a nominal rate of the oscillator. So some oscillators will hold 24, 48. I've seen them go longer than that. Just depends on what you have and what good, what great condition your oscillator's in. The PRS, or the primary reference source, equipment that provides a timing signal whose long time accuracy is maintained at 1 × 10 to the 11th Stratum 1, or better with verification to coordinate UTC, and whose timing signal may be used as the basis of reference for control of other clocks. So this is what I was talking about from the last slide. Usually you have some time source. I listed some here, cesium, GPS, the packet PRS, which is a internal one Metricom uses. There used to be the Loran-C. That one got turned down in 2010. They don't really use that anymore. And of course, CDMA, and there's a few CDMA time sources still out there. And then usually connected over to your time source gateway. The timing signal generator, this is actually what's going on within your clock itself. The input card is where the time source is connecting. So here, you would have the input card, you have your clock card A, and your output cards where your clients or customer base connects to. Timing distribution inside the office, holdover, and redundancy. So time source comes in the input clock. The clock, again, facilitates oscillation. Output cards are connected out to your customer or your equipment, be it some kind of SONET box, DWDM box, whatever. Also, these boxes can connect to alarm, Falcon light systems, the old Telecom Bell systems, and so on. And then, of course, filtering on FL or PLL. One of the advantages of having this stuff is you can put it right in your network, connected to your SONET or DWM. And this is one thing for synchronations of DS1, DS3 circuits is the building integrated timing supply or system today, heartbeat of the network. And you can see this unit is connected in, and you can control things from the central office. You have your PRS that's to provide your Stratum 1, and then you would connect directly to the bits box itself, DSLAM, PON, and so on. Channel banks. You've probably seen maybe this stuff in your building, but didn't know what it was. But all your units are connecting to this, and for synchronization of those circuits. Again, without it, your equipment's going to have a hard time syncing up unless, like I said, it's got Stratum 3E type device in it. So in the SONET, T1 tributary mapped into the clock of the SONET network. Frequency offset results in slips if the SONET network and T1 network are not wireless synchronous. And slip buffers used to compensate for frequency offset and loss of corruption of data. Asynchronous T1 tributary map maintains source clock of the T1 network. Frequency offset between T1 network and SONET network generates BT1.1 pointer movements, but to slips. The frequency offset justified by bit stuffing, and of course your BT1.5 pointers equal jitter. You've probably seen this as some of the people are using their T-birds, testing out a circuit, usually getting a lot of jitter, slips, so on, and problems in the circuit. It's usually connected to some timing problem going on in your circuits. Here's a breakdown of SONET, if you haven't used it, and how it's working. You're working in your protect circuits, connect through. There's your clock connected, your PRS to the TSG, connected to whatever you have, your ADTRAN or your SONET box. Line timing, again, the other units that connect out of the head end. Usually at the head end, if we took this drawing, my head end would be the first one over in the upper left, and line timing would be my other units across the line going across, let's say a fiber ring or so on, to connect my SONET units, and they would connect via line timing, trying to connect back to the head end unit at the upper left. So you got primary timing, secondary timing, and your input connection points, which would be at the head end at this upper left. So my clock would be connected up there. I could pass timing from my head end box and then to these others through line timing. And there's also, you can do some external timing stuff as well. Other specific modes, loop timing for SONET terminals, through timing for unipath, switch rings, and internal timing for point-to-point applications. So again, just a way to get the basic bits around in the SONET world. This drawing here shows you what happens when timing degradation happens. So your technicians have been on doing T1 type work and seeing these slips. This is what these slips in the network, this is what they're seeing along the way. Frequency lock loop control, direct digital synthesizer, NSS provides mechanism to filter short time instability on cascaded timing circuits. And you can see most effective with long time constant made possible by a rubidium oscillator because of its exceptional stability. So in this drawing we can see again, here's our head end, we're going through our line timing. The line timing gets very degraded as we're going to the very last of the drawing. And then it's trying to, it will sync. And you can do things, internal office timing distribution, hold over redundancy filtering. And the other box at the end could say, hey, I can now go over and get derived timing from another box. If this other clock wasn't there in your far right-hand corner, you would divert to free run or hold over timing in the box. That's what we talked about earlier. Synchronization integrity impaired. So here's some of our issues right here. TDM timing issues. Short time instability, jitter, wander, phase transients, thing called MTIE and TDEV. Long-term accuracy, frequency offset, phase frequency, and what you will see, and this is what our technicians see. Bit errors, slips, pointer activity, holdover, and clock alarms. Again, poor synchronization and most common, non-obvious cause of service degradation. And like I said, I've seen networks just actually stop at this point if the errors are just too bad. I'll put this next slide in because as we're moving toward packet timing issues, you can see in the packet world there's some similarities. Packet jitter, PDV, asymmetry, time phase for time transfer. This is really apparent in some of the new things for the high frequency trading networks when they're dealing with time. Of course, latency or delay, packet loss, or NTDV and MRTIE. Network Time Protocol, NTP. Internet Protocol for synchronizing system clocks via timestamps over a packet network. Uses UTC as a reference from GPS constellation, IP client server architecture, timestamps delivered via LAN and WAN. Developed in 1985 at University of Delaware. Air traffic control was one of the first applications. So as you're flying around on the planes there, you can think about NTP as work for you. And widely employed in information technology domain, e.g. every PC. Telecom NEs with NDP clients include soft switches, routers, IP transport, and mobile switching centers. Here's a diagram on how NTP works. Your network synchronization, again, frequency, free run, loop. Here's our Stratum ones as we move through this world, and you can see kind of the DS1 side as opposed over to your network side. Got a lot of the G dots are in this, and again listed through from Stratum 1 through 4, most accurate, least accurate, as I was saying earlier. If you can get Stratum 1, use it as best as you can. Again, I know a lot of operators use 3E, but if you can get to 1, it's a better deal. On the NTP side, there is a Stratum 0, which they include on the antenna side, the antenna being your Stratum 0, and then of course Stratum 1 down. The other thing in NTP, the distant number of hops from Stratum 1 are involved as well. I made this drawing because I've been talking to a lot of network operators now who are trying to move from what's called enterprise NTP to more of the carrier class NTP. And the reason, I asked them why, and they said their servers are failing. Their NTP Unix servers are failing. And they've been wanting to go to a more carrier class NTP solution. Makes sense if you think about it. Most of the NTP clocks today have dual oscillators, and so they would fail over quite nicely. A little bit of more issue on the server side. So again, you can see here some of that in the list. The accuracy, enterprise installation, traceability not assured, not secure, authenticated, spoofing, not designed for mission critical apps. As opposed to the carrier class side, high performance, high accuracy, UTC traceable, 5 nines availability, reality, and reliability, security and authentication, management and monitoring, good OSNPs there, suitable for mission critical applications. So I've been seeing a lot of movement toward the carrier class NTP of late, even with my own colleagues at my facility. Here's a kind of a drawing just showing some carrier class timing architecture. This box has a primary and a backup NTP server. And you can see some of the uses here with the NTP server blades, and then propagated across the network, used for several things. I have a customer I use that connects, uses all their edge router to a special NTP network I've set up and just used. So again, kind of more movement toward the carrier class timing architecture. Networks are transitioning to IP, if that's no news to you, but again, here's the central office, TDM, as it's moving out this way. Now network sync must transition as well. So again, here's our clock unit, but now we're seeing much more Ethernet in the network. Devices are becoming more Ethernet. I've been seeing a lot new SONET boxes go into Ethernet with DS3 modules connected to switch type equipment. So that's all Ethernet. And again, out to your wireless. And there's my X. He's going away. Frequency delivery strategies. Synchronization strategies here. Of course, your E1, T1 circuits, strategy based on the use of legacy PDA systems. This method is only applicable to TDM networks. Adaptive clock recovery, a vendor-specific bookend solution. You support TDM and over IP services. ACR benefits are not industry standard compliant. I see GPS radio, good performance, supporting wide range applications. Cost, vulnerability, and maintenance issues limit wide-scale use. Synchronous Ethernet, an end-to-end solution that mirrors and is substitute for the physical layer, frequency distributed schemes of SONET SDH. So what I just mentioned, I've been seeing a lot of this coming around from the SONET world, going over to SYNC-E for short for that. Of course, the IEEE 1588, 208, the new PTP, layer 2-3 time transfer technology that can deliver frequency and time, and this alternative to SYNC-E for frequency distribution. I think that's a dummy. Also, I want to mention on the PTP, I've also seen this going to the high frequency trader networks as well, being used in their area. Again, because of low latency that they need for their use in their equipment. The IEEE 1588-208 profiles is very interesting. When I first saw PTP, nobody had told me there was all these different profiles. We had some equipment in, and I was talking to some engineers one day, and they said, well, that's great, but you're using the telecom profile, and we need a different type profile. So this is building. I just came back from a meeting about a month ago at NIST, and there was a bunch of PTP programmers there. They're even going to build more things in the IEEE world. Right now, I got default, telecom. I think I have some more here, and also power and wireless. Yeah, here we go. So the default profile, which I've seen more used in the LAN application and used with the high frequency traders. Telecom profile, again, telecom WAN applications. Power profile defined by the IEEE, and again, you can see all the numbers here, you can read these. And like I said, now just even the LTE-based PTP stuff coming up. So what is it? IEEE 15 is a protocol that enables precision distribution of time and frequency over packet-based networks. IEEE 1588 was originally for building and factory, and version 208 contains enhancements for telecom networks, so the telecom profile was thought about. The server clock sends a series of messages to slaves to initiate the synchronization process. Clients synchronize themselves to the server. Network equipment manufacturers are building slave clients into their latest equipment, IP, DSLAM, OLT, eNoBs, and of course LTE base stations. IP sync timing with IEEE 1588. Any service where synchronization over Ethernet is needed, such as wireless Ethernet backhaul, base station again below, packet PRS, primary reference over IP equivalent of derived OCN, -N, and enterprise applications requiring synchronization. And that's kind of what I was trying to show in this drawing here. How is the precision possible? Well, through message exchange technique. And this is where frequent sync messages broadcast between master and slaves and delay measurement between slaves and master. Hardware-assisted timestamp leading edge of IEEE message as it passes between the PHY and the MAC. Removes OS and stack processing delays, and then uses the best master clock BMC algorithm. So I don't know if you can see there in my drawing as your microprocessor is working, your timestamping is happening, Ethernet MAC, Ethernet PHY, and then out to the LAN. Also in 1588, things are known as your grandmaster or the master clock, and moves on through things. You can set up boundary clocks, transparent clocks, and I'll show more of that. Here's your traffic impact, message packet size. These are some of the packet size as this information is passing through. You can see the byte size, signaling announced, sync, follow-up messages, all the sizes. Inbound traffic rate uses the following typical values: announce interval, sync interval, least duration delay, and delay response, delay request date response. Peak traffic transmitted in 1 second. There's a little math formula for you. You want to use that? FASTI and GIGI. So introducing the IEEE 1588 elements. Ordinary clock. So here's where you have your grandmaster and you have a slave, whatever client that's going to be. Could be servers, could be whatever. The interesting thing is this is all over layer 2, layer 3. So you could have what's called the boundary clock, which is usually a switch type device. And Cisco and Arista have made switches now that understand PTP and can become boundary clocks. So they regenerate the PTP message, eliminating earlier path delays. So yes, switch with a built-in clock. It's very interesting. And usually this is usually done over multicast, a multicast setting. You can do the transparent clock, adjust the correction field in the sync and delay event. Switchability to measure packet residence time. I haven't really ran into anybody yet who's using the transparent clock, but I have seen a lot of use of the boundary clock. Of course, management node, human interface to the PTP management messages for monitoring. On-path support transparent clock, switch not a clock, measures 1588 packet delay inside the switch, modifies as resident time to the correction field in the 1588 message, limited to non-encrypted networks, correction field must be accurate. The boundary clock, switch with built-in clock, internal clock synchronized via 1588 to the upstream master, regenerates 1588 messages, slave on one port, master on the other ports, interrupts the sync flow, and the burden of holdover reliability and traceability is on the boundary clock. So you can see from these drawings kind of the difference between the transparent as opposed to the boundary clock. 15, a little message review. The Grandmaster service sends the following messages: signaling, acknowledge TLV, negative acknowledgement TLV announce, sync, follow up, and delay. Message entering the PHY on the on-time marker. Slave client sends the following messages: signaling 3 types: request, announce, request sync, and request delay response, and delay request. Here we go. Multicast, Grandmaster broadcast PTP packets to a multicast IP address. Switches and routers with IGMP snooping forwards multicast packets to subscribers, else traffic broadcast to all ports. Multicast Synchronization, I don't know what happened to my drawing, default profile. This just kind of shows some different things. Sorry about my drawing, got messed up there. I've seen the PIN mode used for the multicast on this, and in the boundary clock, what I've seen is people kind of doing /30s across the port and then pass this back static route to the clients or whoever going to be the slave. So basically people doing PTP servers, clients, or even a switch at the other end. I've actually seen a person, HFT customer, do BGP right through for their PTP connection on their side. Again, since we're in the layer 2, layer 3 world, it was possible and was experiencing low latency. So I was very surprised. The other side of this is unicast. Grandmaster sends PTP packets directly to the PTP slaves. Switches and routers forward PTP packets directly to the slaves. Unicast sync interval telecom profile, and user-defined sync interval up to 128 hertz. Many subscribers supported. So the multicast really I've seen with the HFT as well, but the unicast more with the telecom profile. But don't mix. Don't do unicast with the multicast. Not good, not good. SLA for PTP Flow, bandwidth capacity, minimum 1 gig. I have seen people doing PTP with FE, with an FE port. Maximum loading, 80% average. Internet congestion, 100% load for less than 100. QoS, highest priority, you can go. Hop count, frequency 10 hops. Time 5 hops. Switch attributes, hardware forwarding, QoS. Jitter, highest priority, traffic, QoS. And you can see there 250 microseconds to 10 milliseconds. PTP client algorithms use only a fraction of total packets. The ones with the best quality are low PDV. Packets with high PDV are not used. So high jitter can be tolerated if the distribution of the jitter includes sufficient high quality packets. I also want to mention, I've seen in software, jitter can, if you have a bad OS, just cause a lot of problems in jitter. So you want a really good tested OS if you're going to be dealing with PTP. Syncy, what is synchronous Ethernet? Schema that transports frequency at the Ethernet physical layer. Implemented in the IP transport element hardware, i.e. Sync E enabled. End-to-end scheme, similar to SONET. Sync traceable to Office PRS. All switches must be Sync E enabled to transport synchronization. And of course, ITU2 and the different G dots here define synchronous Ethernet. So you can see here in this diagram how this works. You would again have your PRS, your clock, Sync E switch, and then all the switches in that line have to know about Sync E for them to perform. and then there to your TE1 service. How is SyncKey different from normal Ethernet? Standard Ethernet 5 physical layer. Receive uses the incoming line time. Transmit uses the built-in 100 ppm clock. No relationship between the receive and transmit. SyncKey 5 physical layer. Receive disciplines the internal oscillator, 4.6 ppm. Transmit uses a traceable clock reference, creating end-to-end scheme. And as with SONET, the PRS provides the reference. So again, you're just bringing what you were doing in the bits days with SyncKey to the Ethernet side. And again, you must have SyncKey enabled or SyncKey aware switches involved. And SyncKey standard Ethernet cannot be mixed. So don't I've seen somebody do this. Don't put a SyncKey switch and an Ethernet switch in there and go, where's my time? Where'd it go? Well, you have a standard Ethernet switch in there. It's got to be SyncKey. Here's some synchronization impact. Application, LTE. This is just kind of a chart I put together. Frequency, 16 ppb, phase, handoff, impact. I'm not going to go through all this, but this is just some information you can see on the impact of synchronization. Again, LTE, had a lot of LTE I've been working on. Frequency and time specifications, application, frequency and phase with GSM, CDMA, STD, LTE. Just started doing some research with LTE. And that's it of my talk. Questions? Comments? Yes, sir.
The timpanist, who sits in the back of the orchestra, actually is one of the highest paid people in the orchestra, precisely because he hits the beat an eighth of a beat in advance of everybody else, so that by the time it propagates to the front of the orchestra at a speed of 1 foot per millisecond in air, it comes out synchronized.
Well, you know, what's interesting in that talk with Leonard Bernstein, he said his baton, think of it as light moving faster than audio.
Well, that's exactly right.
Right? But thank you. I like those numbers. You like my formulas, right? Any other questions, comments? Network time is kind of that weird thing. You need it, but nobody knows. It's like when I'm filling with the boxes, people wonder, what am I doing? But then just as soon as they need the syslog stuff to sync up to something. So how many people are using clocks in their network? Can you show of hands? No? NTP? Bits? SyncKey? PTP? Oh, one guy. All right. Well, thank you. Thanks very much.